Hey guys, how's it going? So today in our Calculus 2 lesson, we're going to be going over something called volume, specifically volume about a figure when it's rotated about a certain axis. Now here we have a problem. There's a triangle bounded by the region R. It has the coordinates 1, 2, 1, 0, and 2, 1. And this is R that's bounded. And we want to find the volume when A, it's rotated about the x-axis, or B, it's rotated about x equals 2.5. So how do we do this? That's actually a very good question. First of all, you should know that volume is the integral of area, and it can be from A to B with A of x dx, or from A to B with A of y dy. And the formula for area is equal to pi times the outer radius squared minus pi times the inner radius squared. So we find the area first of the place we're rotating, find these radiuses, and then put them into the formula. So let's tackle each situation separately. I'm going to draw a separate line here. Rotated A about the x-axis. So let's draw the line here. So it's rotated like this. So I'm going to give you a visual representation of it. This is what happens during the rotation. It's like spinning around like this. Yeah. It's just like it's spinning around a revolution. We want to find the volume of that revolution, basically. So the other question, I said V is equal to either with respect to X, the integral for area, or with respect to Y. So how do we know like whether to use A of X or A of Y? And there's actually a rule of thumb for that I'm gonna write down in text. You see, I'm gonna write it along as I go. When the line you're rotating R on is horizontal, or in other words, Y is equal to A, where A is any real number, you integrate the area with respect to X. When the line you're integrating on, you're rotating R on is vertical, or X is equal to A, integrate the area with respect to Y. This is always true. So here, we're rotating it about the x-axis. And when you're rotating it about the x-axis, that's equivalent to rotating it to y is equal to 0. That's the line we're rotating R about in this question. So we're going to be using it with respect to X. So first of all, let's use the formula. A of X is equal to pi outer radius squared minus pi inner radius squared. And before I figure out the outer and inner radius, let's redraw this diagram. This time with just the x-axis, or y is equal to 0. Okay, so let's see. You can draw the y-axis if you want, but it's not going to do much help here. I'll just label it y for sake. So here, I'm going to call this L1, and this is L2. So yeah, this line here is L1, and this line here is L2. I want to parameterize these as functions with respect to x. And I'm going to label these points 2, 1, 1, 2, and 1, 0. L1 is like connecting the points. The first line is connecting the points 1, 0, and 2, 1. And with respect to x, that is expressed as a function y is equal to x minus 1. That's the line that connects these 2 points. L2 is with 1, 2 to 2, 1. And the function for that is y is equal to 3 minus x. So we have these 2 functions that expressed in these lines. Now we're rotating it about the x-axis, or y is equal to 0. The outer radius is going to be the line that's further from the x-axis, which is L2, which is 3 minus x. So that's pi 3 minus x squared, since 3 minus x is the outer radius, it's further apart, and minus x minus 1 squared. So hopefully you had a good chance to look. I'm not erasing the whole thing, just this part. Okay, so now we can do v. So v is equal to the integral of b a sorry there. A of x dx which here it's obviously from x equals 1 to x equals 2 with this figure. So b is 2 and a is 1. And a of, okay, so I'm going to put the pi outside here. We're going to be using this as our a of x. Three minus x squared minus x minus 1 squared dx, which is equal to pi from 1 to 2 x squared minus 6x plus 9 minus x squared plus 2x minus 1. Let's simplify this. The x squareds cancel out here. And this is 8 minus 4x. So that's equal to pi 2, 1, 8 minus 4x dx. V is equal to 2 to 1 there's this slight dot here that's kind of bothering me. The antiderivative, so 8x minus 2x squared from 2 to 1. And that is equal to pi. Okay, so when x is equal to 2, that's 8 times 2, 16 minus 2 times 4. That's 8. At 1, that's 8 minus 2, which is 6. Your answer is 2 pi. And this can also be verified with another method called using cylindrical shells, which I will explain in a separate video. But yeah, 2 pi. So part A is done. Let's move on to part B. Part B is slightly trickier, but it's not that bad. Let me explain it. So B, it's about x equals 2.5 this time. It's a line. It's slightly different, but the concepts are still the same. As long as you understand the concept in math, no matter what problem you're given, you should be able to do it. So here we have our y, here we have our x, and I'm going to label this. So we have our points. This is obviously not drawn to scale. All right. Let's also mention first that, okay, so let's also draw our line here. This is the x equals 2.5. Since this question involves rotating about a vertical line, this time we're going to be using a of y. We're going to express the area as a function of y. So let's write down the formula first. A of y is equal to pi outer radius minus inner radius squared. Outer radius squared minus inner radius squared. And here we have this, we have two lines. I think this was L1 and this was L2. It doesn't matter the ordering, but yeah. So L1 I expressed was y is equal to x minus 1 in the previous question, right? And when I did part A, we said that this L1 was parameterized by y equals x minus 1. Let's parameterize this with respect to y this time. So that implies that x is equal to y plus 1. L2, y is equal to 3 minus x. Let's see, so then that's x plus y is equal to 3. X is 3 minus y. These are the two parameterizations. Now, this. You guys got to see this, right? I'm debating if I should erase this because like I have it in my notes, but I'm running out of space here. You know what? You guys take. I'm gonna give you guys about 5 seconds to take a look at these two parameterizations. Actually, wait. No, I'm gonna keep them because it's gonna explain what's going on next. So the outer radius is equal to so let's take a look here. The outer radius is this line x equals 1 because it's farther located from x equals 2.5. So the outer radius is just 2.5 minus 1 squared. The distance, the radius will be a constant 1.5. So that's the outer radius. Now, the inner radius will depend on like when you're using it from this part L1 or L2. These lines are a little different for the inner radius. So you know what? I'm going to do this instead. Sorry, guys. This is a little trickier, but hopefully we can manage. I'm going to write these lines at the bottom down here. So not equals, colon, yeah. L1. So the L1, and that was x equals y plus 1. And the L2 was expressed as x equals 3 minus y. And we're going to be doing like it from 0 to 2. But the problem here is that the inner radius, it's not a fixed function. There's a line from y equals 0 to y equals 1. And there's a different line from y equals 1 to y equals 2. So here's how I'm going to tackle this instead. I don't need this formula anymore. The formula is expressed up here. So yeah. V is equal to the integral b from a to b, a of y dy, which is equal to, and I'm going to split it up from 0 to 1 and 1 to 2. Okay, so the outer radius, okay, let's do this, the pi, and the outer radius, okay, so from 0 to 1, that's 1.5 squared minus the inner radius, which is 3, let's see, no, so 3 minus y, but it's the distance, it's 2.5 minus 3 minus y. So it's, how do I say this? It's 2.5 minus 3 minus y squared. That is the inner radius for, no, sorry, I'm getting way too ahead of myself this time. Let's see, so 2.5 minus y plus 1 squared dy. Okay, good. Finally. I'm I'm gonna write things down and then I'll explain it to you later. (1.5 squared d). Five minus 3 minus y squared. Okay, so this is the exact formula that we use. So here, in both cases, from 0 to 1 and 1 to 2, the outer radius is 2.5 minus 1, because it's like the line x equals 1. So then, yeah. And here, like from the inner radius is composed of L1 and L2. But the problem is L1 and L2 are different lines, and thusly they are differently parameterized. So for L1, that's x equals y plus 1. So the distance, the radius of this from 0 to 1 is inner radius is 2.5 minus whatever value y plus 1. This is the radius here. So for example, if y was equal to 0, then that's 1.5 minus y, so right? 1.5 minus 0, that distance is 1.5. If y was 0.5 right here, that radius, that inner radius is 2.5 minus 1.5 minus let's see, no, sorry, 1.5 minus 0.5, which is 1. Am I doing it right? Yeah, I'm doing it right. Yeah, and then here it's 1.5 minus 1, which gives you a radius of 0.5. And then here, that's 2.5 minus 3. So that this inner radius is parameterized as y minus 0.5. So then, like, if y was equal to 2, then let me think. 2 minus 0.5 is 1.5, because, yeah, and that makes sense because x equals 1 here and x is 2.5 here. So that radius is 1.5. If y was equal to 1.5 right here, then the y minus 0.5, that's 1.5 minus 0.5, that's 1. And that's the distance of the inner radius there. So yeah, we just broke it down into two different triangles, two different separate triangles, this shape. So V is equal to, you guys know how to do basic math. I'll just simplify this a bit and then just give you the final answer. So V is equal to pi 1, 0, 2.25 minus 1.5 minus y squared. Plus from 1 to 2, another pi 2.25 minus y minus 0.5 squared dy. And to spare you guys from getting bored, although I know this is pretty boring, when you simplify this out and calculate all this, you're going to get an answer of 7 pi over 3. And like part A, you can also verify that this is the answer using something called the cylindrical shells method. So that is it for today. I hope you guys like this video. I will see you guys next time.